Hello, everyone. I am Zhixiong from Microsoft Research. Today, I'm going to present our paper, NetKernel, making network stack part of the virtualized infrastructure. Okay, let's get started. This is the current architecture in the cloud. We have two layers. VM. This is fully controlled by the tenants. And hypervisor and data center network infrastructures, they are fully controlled by the operators. But we think this kind of design has some limitations. We will introduce the problem in two aspects. First, for the tenants, if some tenants have some special requirement for the network stack, they may need to tune the TCP parameter. For example, initial congestion window, initial RTO, min RTO, and delayed ACK timeout, and also some kernel parameters. For example, socket buffer. And if they have some special requirements, they may need to install advanced congestion control algorithms and user space networks. In summary, the tenants have to deal with the things regarding network stack all by themselves. But in fact, the tenants are primarily concerned with the performance and the functionality, not the implementation details. On the other hand, for the operator, actually, they know everything there. They can really help their tenants and also make some money on that. They have enough resources, including the experts and expertise. They know everything regarding the network, including the Linux kernel, RDMA, FPGA, NIC, and DPDK. However, for the hypervisor, there are some nature boundary between the provider and the tenant's VM. Because for a provider, they nearly have zero visibility and control of the network stack. For the providers, they cannot deploy new network stacks, for example, DC TCP. If it's difficult for them to define a performance SLA, difficult to perform some measurement tasks, and difficult for them to do the troubleshoot because of the boundary between the hypervisor and the tenant's VM. Is there a better way to solve this problem? Actually, our answer is yes. Look at this figure. We can see the center of the problem is the network stack is coupled to the guest OS. To solve this problem, our solution is to make the network stack out of the tenant's VM, to make it as a part of the infrastructure and controlled by the provider. The network stack runs as an independent module. We call it network stack module, or NSM. And this is our solution, making network stack part of the virtualized infrastructure. In the tenant VM, we keep the interface unchanged, say BSC socket, and all of the packets can be handled in the NSM by the provider. Now, I will introduce some benefits if we can achieve our idea. For the operator, we can achieve better efficiency in management. For example, we can orchestrate the resource provisioning strategy more flexibly. And also, we can implement the management function as a part of users' network stack. And for the users, they can have deployment and performance gains with nearly no efforts. They can enforce various kernel stack optimizations and high-performance user space stack. And also, they can use some advanced hardware to achieve this. To realize our idea, we have three main challenges for us. The first one is the user won't like to change their applications. Can we transparently redirect the socket API calls without any change on the applications. The second one is the VM and NSM. They need to communicate with each other. How can we create a channel to exchange the socket semantics? And the last one is, how can we ensure the high performance with our semantic transmission in the modern data center, say 100 gig? So now we will answer the questions one by one. First, we create a new socket type in the guest lib inside Linux kernel. This is a complete implementation of the BSD socket APIs. In the Tenants VM, all of the system calls will divert to NetKernel APIs. For example, the socket will be diverted to NetKernel socket. The socket send message will be diverted to NetKernel socket send message. For every network functions of the BSD socket, the guest lib provides the same APIs for the application in the Linux kernel. And as you know, the application works in the user space. Hence, it works without any changes. We also provide a lightweight semantic channel between the VM and NSMs. For the socket semantic, we provide NQE, NetKernel queue elements. Each NQE is 32 sized. It contains the operation time, VM ID, queue site ID, VM socket ID, operation data, data pointer, and the size of the data. For each BSD socket operation, the guest lib will translate this to NQE and put them into the queues inside the NetKernel devices. The guest lib also checks if there is any new response NQE from the NQE queues. If yes, the guest lib will process the NQE and do corresponding operation, and then return to this app. And by the way, the queues are only for the metadata. We also have huge pages in the NetKernel devices for the real data transmission. To make the NetKernel scalable and achieve very high performance, we also designed the scalable lockless queues between the VM and NSM. They are per core basis. Meanwhile, all of the NQE are switched by our core engine. We also put a connection table into the core engine. It can remember the mapping between the VM and NSM. The provider is able to make their own policy to achieve the load balancing and their own SLA for this. And by the way, we use VM-based NSM. That means each NSM is a VM actually. We have 3 reasons to design this. Firstly, it can support existing Linux kernel and user space network stacks from various operating systems. For example, Linux, Windows, and FreeBSD. And the NSM does not need to have the same operating system as the hypervisor or the tenants. Secondly, the VM can also provide good isolation to guarantee the performance of the NSM. And lastly, each network stack can be encapsulated as NSM and run independently of the hypervisor. If an NSM crashes, we can just simply reboot it. There is no need to do other things. After introduce the design highlights of NetKernel, let's see the overall design of the NetKernel framework. As you can see, in the NetKernel framework, we have several parts. Tenants VM, we have guest lib in the Tenants VM. That guest lib can just intercept all of the APIs of the BSD socket and put the socket semantic into the NetKernel device. And in the NSM, we also have a service lib pulling the NQEs from the queues and call the real network APIs from the network stack in the NSM. They also have NetKernel devices. In the devices, we have queues and huge pages. Queues are for the metadata exchange, and for the huge pages, they are just for the data exchange. And all of the queue elements actually are switched by the NetKernel queue engine. Actually, we also have VNIC to attach the NSM, and the packets go through the VNIC to the virtual switch or embedded switch, and then finally go to the PNIX. After finishing the design of NetKernel, we realize our NetKernel on the Linux KVM. We use a machine with 20 CPUs and 256 GB memory. And this machine is also equipped with Mellanox 100 GB single port NIC. After discuss the design and the implementation, let's discuss the first use case of the NetKernel, multiplexing. As you can see in the figure, this is the normalized RPS performance of a trace from a large cloud. In the figure, the three AGs can achieve their peak performance in different times, about 8 minutes, 15 minutes, 25 minutes, and 55 minutes. To serve the peak performance, each AG needs to be equipped 4 cores. But if you adopt the NetKernel, you may use less cores. You can do in this way. For each AG, you can assign 1 CPU core for the application logic, and the NSM can be equipped with 5 cores to handle network connections. Of course, you need to assign 1 core for the core engine to switch the NQE between the NSM and the VMs. So you use 9 cores in total. In the experiment, you can see, since you assign less cores to handle the same traces, the NetKernel can increase the normalized RPS per core. So the NetKernel can help operator perform network management more efficiently. In the second use case, we will show how to deploy the mTCP without any API change in NetKernel. So far, in the original mTCP, they don't support the nginx yet. So we port the mTCP as our mTCP NSM. During porting the mTCP, we also found a bug in the DPDK Mellanox driver. I think it's very hard for a tenant to do this. And finally, the tenants can use the unmodified nginx on mTCP without any tenant's effort. And you can see in the figure, we can have performance gain in all CPU configuration. And in the 4 vCPU scenario, the mTCP brings about 1.8 times performance gain. In the third use case, we provide a shared memory networking for the inter-VM communication. Since with NetKernel, the operator can easily detect on-host traffic with NetKernel. It uses a shared memory to avoid TCP and bridge overhead. Compared with the baseline, we can see when the message size is 8K, the shared memory can achieve more than double performance gain for the on-host traffic. So in conclusion, NetKernel can help users to achieve deploy and performance gains with nearly no efforts. And we also did some macro benchmark on the throughput and the RPS for NetKernel. We compared the baseline and the NetKernel use same setting, 8 TCP connections, and the message size is also 8 KB. We can see the NetKernel can achieve the same performance of the baseline. They both can achieve 100 gig in 8-core receive and 3-core send. And we also benchmark the RPF performance of the NetKernel. We test the NetKernel with a simple IFO server with short TCP connections. For 64 requests and response, the mTCP brings nearly double performance gain in 8-core scenarios. For another CPU number, we can also have some performance gains. But we are so sorry that we didn't run mTCP successfully when the number of CPU equals to 3, 5, 6, 7. So we didn't provide this kind of data here. After introduce the performance results of the NetKernel, we will also have some discussion on the NetKernel. First, how can we do the net filter? I think the general answer of this question is, it is hard for us to spot it. It is because we move the network stack out of the VM. All of the packets processed actually are in the NSM, and the user has no control on it. If this is a single tenant NSM, it is possible for us to provide some callback function to enable the net filter for users. But for multiple tenants NSM, it is really hard for them to do this kind of thing because the privilege control for this is really hard. We suggest in this kind of situation, the user should use the traditional architecture for the net filter. And the second question is, what about the troubleshooting for the performance issue? We believe this is one of our benefits of the NetKernel. In the traditional architecture, it is very hard for users to diagnose the network since the root cause of the failure is very complex. The problem may happen in the network stack hypervisor and also the data center infrastructure. We believe it is operators' responsibility to do this kind of network diagnosis. With NetKernel, the provider can easily monitor their NSM by deploying additional mechanism in the NSM. For example, Peng mesh. If they find something wrong, they can quick fix the problem all by themselves. And the third question is, does the NetKernel increase the attack surface? Our answer is no. We think NetKernel shares same attack surface as the OVS and the USENIX. For the NetKernel devices, they can have their own address spaces. And if a data pointer is not valid, we will block it. And between each NSM and the VM, we can use the isolated channel. And we also have some future directions for NetKernel. Although NetKernel is already enabled to have some simple isolation, we may need some higher level performance isolation for the NetKernel. Besides the throughput isolation, we may also need the RPS isolation. And I think the charging policy are also very interesting to research. Our question is, how does a user pay for the NSM usage? By RPS, by throughput, or by the core number they use? I think this is need to have some further investigation. And finally, to further decrease the overhead, we can use FPGA or SoC to implement the core engine at the NetKernel devices. Okay, I think this is all of the presentation of the NetKernel. There are some recaps on this. In this paper, we designed and implemented the NetKernel. The NetKernel decouples the network stack from the guest and making it part of the virtualized infrastructure in the cloud. And in this paper, we enabled several new use cases. For example, multiplexing, mTCP NSM, and shared memory NSM. And we conducted the comprehensive testbed evaluation with commodity 100 gig NICs. And our official website is netkernel.net. And finally, I want to say thank you to every audience of this talk. Thank you.